Okay, so series of videos now to get you ready for your March mock. You'll be doing a paper 2. I've got similar related questions in terms of various things that are coming up, and they're organised by units. Now, this is going to be a tricky mock for you because by the time you do the mock, you will not have finished all the units. You'll have done big chunks of it, and you certainly won't have refreshed it and done lots of retrieval practice on it. So this is likely to be a little bit harder than the paper 1 that you did earlier. But anyway, here we go. So P8, got energy and forces doing work, and you've done parts of this in year 9 and 10. So an electric motor transfers some electrical energy, and I can see 1.3 kilojoules. So times that by 1,300 joules in 4 minutes, times by 60 equals 240 seconds. What's the power? And it tells us the formula, energy equals power over time. So we know that this is the PET formula. And then we're away. So rearrange it, P equals E over T. Take the 1,300, do the unit change, take the 240, do the unit change, put that all together, 5.42 watts. And remember, unit for power is watts. Now, watts are the same as joules per second. Okay, so that's the first part there. Next one, we've got a question about a motor lifting masses. You'll remember doing this practical with me because it's tricky. So the basic idea is, well, I get a motor, and then on that motor, I'm going to raise some masses. And the crucial part is I'm going to put some electrical energy in, and that's going to be transferred to GPE. So if I tidy that up here, here's the basic idea. And then the next part is, well, I need the equations for this. So the basic idea is, well, I'm going to put it in this circuit. I'm going to have an ammeter, a voltmeter, and I'm going to have a stop clock. And that's because the electrical energy is current times voltage times time. So I can work out the energy I put in. This is the input, so total input. And then the next part is, well, the gravitational potential energy we know is mGh. And that's going to be the output energy, and that's the useful output. So the crucial parts are, I need to know the current, the voltage, and the time. That'll give me my input. And I need to know the mass, gravity, number 10, and the height, and that's the output. Well, the next part now is efficiency. You can see why this is so complicated. Efficiency equals useful output over total input. So now we can see, well, okay, we've got these here. So in this example now, efficiency is going to equal the useful output. That's my gravitational potential energy divided by my useful input, current times voltage times time. Okay, which is the electrical energy. So now, if I now just substitute these with the formula that make them up, we can see the efficiency equals mGh divided by IVT. So tough, yeah, it's a tricky question. So I'm going to rub all of this out. There's an explanation of what goes on with the efficiency of the motor. If you're stuck on this at all, just give me a shout after school on the Thursdays. So almost finished rubbing all this out. So now, a motor is used to lift masses from the floor. A student wants to work out the efficiency for different masses. Describe the method that could be used, stating what measuring equipment will be required and how efficiency could be calculated. So again, I'm just going to do my notes here. Efficiency equals useful output over total input. This is going to equal GPE divided by electrical energy. And this is equivalent to mGh over IVT. So that's my basics there in terms of just helping me structure this. And there we go. So the input energy is electrical energy. We calculate it using IVT. The output energy is gravitational potential energy, mass times gravity times height. The efficiency then is the useful output divided by the total input, so mGh over IVT. And we can see I've got 3 marks already here. So next part, for my input energy, I need an ammeter, a voltmeter, and a stop clock. That's my I, my V, and my T. For my output energy, I need a balance in order to work out the masses. I need the number 10 for gravity on Earth, and I need a meter ruler or ruler. And then my basic experiment is take at least 5 masses. So I've got 0.1, 0.2, 0.3, 0.4, 0.5 kilogram masses, mark. Measure a 1 meter height with a ruler, because it tells you you've got to state your equipment. Next part, start my motor, start the stop clock, take the reading from the ammeter and the voltmeter. I've missed out parts in it because it's run out of space, but obviously I'll then stop the stop clock, and efficiency equals the mass times gravity times height divided by the current times the voltage times the time. So a very tough question, and I hope that's helped you just understand it, and I will be going over that in the morning interventions and in the after school ones on a Thursday. Okay, next one. It says 250 grams was lifted by the motor and 9.4 joules of electrical energy was transferred. So that's clearly my IVT all worked out for me, so I'm going to need that, and it's in joules. 240 grams though, not happy with that. We've got to divide that by 1,000 equals 0.24 kilograms. And it says, assuming the motor was efficient, what height was the mass lifted? So we can see here, GPE equals MGH. So we're assuming all of the electrical energy went to GPE. So I'm just making that distinction now. The electrical energy is the GPE, because it says assume it's 100% efficient. So we know we're just going to be using the MGH, MGH and GPE. It says what's the height? So we can see H equals GP over MG, this part here, and then I just put my numbers in. 9.4 is the electrical energy that we're saying all went to GPE, divided by 0.24 times 10, and there's the height, 3.92. Why are motors not 100% efficient? So we've got this idea that you've got to talk about dissipated thermal energy that goes into the surroundings. So there is friction within the motor, thermal energy is produced, which is dissipated into the surroundings, and just learn that every time. Dissipated into the surroundings gets you loads of marks. The next one, the student used a light gauge and a data logger to measure the time. Why is this an improvement? So the first part now is we're going to say, well, we're reducing, and the error that we're reducing is systematic error. That is errors to do with my measuring equipment. The other one we've got is random error, and that's just due to the nature of doing it in different places at different times at possibly different temperatures. But because this is about my measurements, this is systematic error. So this reduces the percentage systematic error by removing human reaction times. And you have to state that. You've got to say, I'm removing human reaction times. So in doing that with the stop clock, I've got some errors that I'm introducing. Next one, a box is moved with a force of 820 newtons. We're pretty happy with that because that's already in newtons. The person moving the box transferred 5.8 kilojoules. Okay, we're used to doing this now, times 1,000, 5,800. What is the total distance the box has moved? To 3 significant figures. So again, from last year, fat, wobbly dinosaurs. We want to work out the distance, D. So D equals W over F, and then we're just going to plug the numbers in. So D equals W over F equals 5,800 divided by the 820 equals 7.0731. And then we want it to 3 significant figures. So that's here, using the 3 to round down, 7.07 meters. So I think this unit's quite nice. Apart from the motor bit, the calculations are nice and easy. And that's that done.